Uh, okay. Are we seeing the right screen?
Yeah, I see the presentation.
Okay.
It's not in present. There we go.
um, so let's talk about resistance. We talked about voltage and current the previous session. So basically, the other component is resistance. And the actual definition, uh, they defined an ohm as a unit of resistance, as the electrical resistance between 2 points of a conductor when a constant potential difference of 1 volt applied to those points produces in the conductor a current of 1 ampere. And that little thing on the end is the conductor not being the seat of any electromotive force. In other words, there's no other voltage in the circuit. So that's kind of the formal definition of Ohm's law. The formula that you need to get familiar with is resistance is equal to the voltage or the electromotive force divided by the current in amperes. So it turns out it's a ratio of volts to amperes. And the way Mr. Ohm determined that was just a lot of experimentation. And he sampled various materials and set it up and applied a voltage across it and measured the resistance. And he did that for multiple values. And for each material, it turned out that that plot was a straight line. It was a constant ratio. So that's kind of how he derived his Ohm's law. Now, and a lot of times you will see that Greek symbol omega, which I think is small omega. And we use that to represent ohms instead of writing ohms out. The basic definition you need to remember is that resistance is the opposition to current flow. And the other important thing, it is frequency independent. So a 1 ohm resistor has the same amount of opposition to current flow for a DC or direct current circuit as it does for an alternating current or RF. Now, that's not going to be the case a little bit later when we talk about things like capacitors and inductors, where they have what we call impedance, which is similar to resistance, but is frequency dependent. And in most cases, you're going to have a combination of two values, the resistance or the real resistance plus as part of the impedance equation, a reactance component, which is the opposition to current flow in a capacitor or inductor. This is just a thing showing how Ohm plotted it, and you can see Ohm's law is just the slope of the line. It's the ratio of voltage to current. There's what we call a pie chart, which a lot of people use to remember Ohm's law. the way it's supposed to work is you draw a circle, divide it in half, and then divide one of those halves in the quarters. You put E for electromotive force or voltage on the top, and you put I and R on the bottom segments. So if you want to solve for, let's say, E, you would put your finger over E, and it leaves you with I times R. If you wanted to solve for current, you'd put your finger over the I, and the formula would be E divided by R. Likewise, if you wanted to solve for R, you put your finger over the R and you get E divided by I. So it's a very graphical way to remember it, although those three formulas are pretty simple. And as long as you remember resistance is equal to the ratio, or E divided by I, this simple algebra you can manipulate and get the other two. Some examples. So we defined an ohm as 1 volt per ampere. So a volt is therefore 1 amp ohm or product. And an amp is therefore 1 volt per ohm. So it's just different ways to say those three equations. So if we had, for instance, a 20-volt source providing 2 amps, and we want to know what the resistance was, we just divide the 20 by 2 and we get 10 volts per amp or 10 ohms. And I don't know if I mentioned, we call them ohms because of George Simon Ohm, who discovered Ohm's law. In the next example, we've got 2 amps flowing through a 10 ohm resistor. So that's 20 amp ohms or 20 volts. And the third one, we have another 20 volts applied to a 10 ohm resistor, and it's going to give us 2 volts per ohm or 2 amps of current flow. So these are all really simple. These are the kind of questions you'll see on the technician exam. This is just a picture of one of the very early resistors. This was a 1 ohm resistor from 1917, big can. Everything was big back in those days. Today, this is what an assortment of resistors look like, where we have some power or wire wound resistors over on the right, all the way down to either carbon or metal oxide films. They were becoming very small. I don't have any surface mount on here. They'd be hard to see. Almost look like a grain of sand compared to these. There's a color code table that's used to mark the values of resistors. It's called the RETMA color code, the Radio Engineers and Technology Manufacturers Association or something like that. It was done decades ago. And we use these colored stripes on the resistor to indicate its value. And each one of those stripes will have one of 10 colors. think I'm covering up the bottom down here. So black is represents 0. Brown is 1, 2 is red, looks kind of orangey. 3 is orange, 4 is yellow, 5 is green, 6 is blue, 7 is violet, 8 is gray, and 9 is white. So the way you would read those is the first 2 stripes is your numerical value. The third stripe will be a multiplier. So they're showing what? Green and I'm assuming that's red. Or excuse me, not green, blue and red. So that's going to be 6, 2. The multiplier is black. So that means it's times 1. So that would be a 62 ohm resistor. Now you see a fourth stripe out there, which indicates the tolerance for that particular resistor. Most of the common ones are going to be 5 or 10%, where the 5 would be yellow and the 10, I know it's hard to see, is actually going to be silver. Actually, that 5 is more like gold. In the case of very high precision resistors, you're going to see some different tolerance values there for 1 and 2%. They're not all that common, but they do make them in high percentage, high tolerances. So if you actually get into building equipment or even working on it, modifying it, one of the things you'll need is this color code table, or just remember it. If you use these things enough, you'll remember this.
Robert, question.
Okay.
Is that on the technician exam, knowing how to do that?
No.
Thank you.
I'm trying to tell you stuff that's not on the exam that you need to know.
Good enough.
One of the most common tools that we use to measure resistance is the common multimeter. And they can measure ohms anywhere from down to 1 or 2 ohms up to multiple megohms. That's about all you see anybody use anymore. It's unusual to see actual laboratory meters for measuring ohms or voltages or currents. Here's some kind of a typical Chinese multimeter that you can get today for 30 bucks. This one might even be more because it supposedly has true RMS, which we'll talk about a little bit later. Over on the right is what's called a Wheatstone bridge, which is what they used to use in the laboratory. Maybe they still do. And you actually have a circuit of 3 fixed resistors. I shouldn't say 3. 2 fixed and 1 variable. And you put the resistor you want to test in that little bridge circuit and adjust the variable resistor until you balance the bridge. And whatever that value, when you adjust those knobs for the variable resistor, that's going to be equal to the resistor you're testing when the bridge is in balance. So what is the definition of resistance? And this is on the test. the opposition to current flow. What is direct current? It's called direct current because it always goes in the same direction. It does not reverse. Whereas alternating current reverses direction. Current goes back and forth. What's the most common source of a constant DC voltage? Either a battery or a power supply. What's the most common test instrument for measuring voltage, current, or resistance? Common multimeter. Any questions on those?
No, I'm good.
Okay. There's a lot of questions like that that are not where you have to do a formula. It's just definitions of things. Here's some examples. So we got a 12-volt and these are the kind of questions you may see on the technician exam on the Ohm's law part. So I've got a 12-volt battery supplying 2 amperes. So what's the resistance of the load in ohms? So how would we work that? We want to find R, right? So if we put our finger over the R in the pie chart, we get E divided by I. And we know E, and we know I. So 12 divided by 2 is going to be 6 ohms. So if I've got a 10 ohm resistor that has 1.2 amperes flowing through it, what is the voltage across it? So if we go to the pie chart and we want to know what the voltage is, remember we put our finger over E, so that leaves the bottom, which is I times R. So I is 1.2, R is 10, E is 12 volts. We got 12 volts across a 4 ohm resistor. What is the current? So once again, we put our finger over the I, gives us E over R, or 12 divided by 4, or 3 amps. These are all pretty easy, as long as you remember Ohm's law. And remember, in this, very good chance this question will come up. Resistance is the opposition to current flow. And it's just a fundamental thing you need to know. It's the ratio of volts to amps. So that's why R is equal to E over I. And we measure it in ohms. Sometimes we represent it with the omega sign. And once again, if you have trouble remembering it, just try to remember to draw your little circle. Okay, so power is the next thing, and it's the actual rate of doing work, and we measure it in watts. And that was named after a Scottish guy who had a lot to do with steam engines, James Watt. We call power, we measure it in watts. Work is the amount of energy that's used, and we measure that in joules, which is a watt second. In other words, if we do we have power of 1 watt for 1 second, that's going to be 1 joule of energy. Now, you don't need to know that for the technician exam. But I'm just trying to show you where this stuff came from and how we get the power formula. So I was trying to show you how you derive it there. The bottom line is that power is equal to the voltage times the current, or the force times the amount of current flow, or coulombs per second. We can use substitution and convert that power to a formula of power is equal to I squared times the resistance, or E squared divided by the resistance. I believe there's questions on those on the technician, definitely on the general. So if we had a 50 ohm resistor and it has 70.7 volts across it that we measure, how much heat is being dissipated? In other words, how much power? So we want to find P, okay, and we know R and E. So we can use the formula P is equal to E squared over R. So I take 70.7, square it, divided by 50, and I come out with 99.97 watts. The reason I use those numbers, that's the typical output of a amateur radio transmitter, 100 watts. So even though it might be supplied by a 12-volt battery or a 13.8-volt power supply, it's going to have an output voltage of 70.7 volts into the antenna. And that's going to be 70.7 volts RMS, which we'll talk about in a little bit. But that's the equivalent of DC. If we had a 100-watt light bulb and we connected to a 120-volt AC source, how much current is going to be drawn? So we know that the power is 100 watts, and we know the E is 120. So we want to solve for I, and power is equal to E times I, or I is equal to the power divided by the voltage, or 0.833 amperes.
Robert, I've got a question for you.
Okay.
It's kind of a mixed question, so bear with me. I was reading up yesterday on connecting different transmitters to antennas.
Okay.
And it said you have a 50 ohm. It recommended, I think this was like a single-ended antenna or something, and it was talking about having a 50 ohm resistor between the connector and your transmitter. And so would those components have, when you buy them, would they have a rating of what kind of wattage they can take?
Are you talking about antennas?
Well, I was talking about the little connector between the transmitter and the antenna, and it said, okay, you need a 50 ohm connector between your transmitter and the antenna.
Okay. Most amateur radio equipment, I'd say 98%, are built to have a 50 ohm source impedance.
Okay.
Okay. So they need to be connected to a 50 ohm load. In other words, your source has to match the load for maximum power transfer.
Okay, the load being the antenna
load being the antenna.
and all the gubbins that goes with it.
So, and you normally connect that with what we call a feed line. Typically, it's going to be coax. It could be ladder line or twin lead. In the case of coax, even though there's some 75 ohm used for cable TV mostly, most of the amateur radio coax that you're going to use is 50 ohms. That's its characteristic impedance. What that means, if you took an infinitely long piece of coax and put a ohm meter across it, it's going to look like 50 ohms if it's infinitely long. Now, obviously, you're not going to have an infinitely long piece, but that's how the characteristic impedance is developed, because the coax looks like a network of inductors and shunt capacitors all along it. So as long as that piece of coax is terminated in its characteristic impedance, like 50 ohms, and it's driven from a 50 ohm source, then you're going to have essentially maximum power transfer through it. You won't have any standing waves or any reflections. In the real world, that's not the case. There's very few antennas that are actually going to be 50 ohms. If you look at your standard dipole, which most antennas are a derivation of a dipole, it's this 2 quarter wavelength long pieces of wire with the feed line connected in the middle. And depending on how high that is above the ground, it's going to be in the 70, 75 ohm range. So when you hook a 50 ohm coax up to it, you're going to have an impedance mismatch and a standing wave ratio of about 1.5. So you need to use some sort of matching network. I won't talk about it now, but we'll get into it when we talk about the radio stuff, on how you accomplish those matches, either with transformers, with stubs, with what we call an antenna tuner. It does not tune the antenna, but it does an impedance match. But back to your basic question on power, the coax is rated for power. So most of the like half-inch coax, like LMR 400 or RG8, I think 213 is the other sort of equivalent. They're rated for 1,500 watts or more, which is the maximum power we're allowed to use. The smaller coaxes, when you get down into like the 1/4 inch stuff, like RG58 or RG8X, I think they're in the 5, maybe 600 watt range. The connectors typically aren't a problem. If you install, and you should, lightning arresters in the feed line, those will have a power rating, because most of them work with a little gas discharge tube that arcs over at a certain voltage. So obviously it's got to be a high enough voltage that's greater than what voltage you're going to put on the antenna from your transmitter. So a lot of them, the cheap ones in particular, will only be rated for maybe 200 watts. The more expensive ones will be rated at 1,500. Was that more than you asked for?
No, that was a perfect answer. I totally understood it and very clear. Thank you.
Okay,
That was perfect. So 1500 watts is what the stuff's rated, and we just calculated what, 70 watts? So I got it.
okay. Um, okay, so the power equations are just like Ohm's law, and you can just use a little algebra to get any one of the three variations, so you can solve for uh, whichever parameter you need. It's been a while since I went through the technician exam. I'm fairly certain there may be a power equation problem. You should know it anyway. Definitely
Sure.
will know it for general and extra. Let's see, we did that one. Okay, so if I've got a 13.8 volt car battery, and we actually use that number because most people think of a car battery as 12 volts. It's actually closer to 13.8 when it has a nominal charge. And that's why if you look at amateur radio power supplies that you use to power transceivers, they're going to be rated for 13.8 volts so that you can use that radio from a car battery and make it mobile. So in this case, I've got a 13.8 volt car battery supplying 20 amps to a radio. So what is the resistance and how much power is being consumed? Well, resistance is easy because we know the volt and the current. So it's just the ratio of 0.69 ohms. The power, okay, we know voltage, we know current. So, and I just worked it three different ways to show that whichever way you do it, the answer comes out the same, or 276 watts. The reason I picked those numbers, that's a typical power input that you're going to see on a 100-watt radio transmitter. If it's putting out 100 watts, it's going to be drawing in the neighborhood of 276 watts from the power supply. And there is a question or so similar to that, wanting to know you have a choice of power supplies to power a radio, and you have to figure out how many watts you need from the power supply. So it's a similar calculation. Okay, so mentioned a little bit about the difference between direct current and alternating current. And when we're talking about direct current power, we're basically talking about the equivalent amount of heat or its conversion to heat in watts. Okay, so if we're running current through a resistor or a light bulb, say in the 100-watt light bulb, it's putting out 100 watts. Part of it is light, part of it is heat, but there's 100 watts going into it. When we talk about AC power, okay, we refer to the equivalent heating of DC because alternating current, like I said, the current alternates and the voltage is typically sinusoidal. So in your 120 volt outlet in your house, that's 120 volts RMS or equivalent to 120 volts DC. So if you put 120 volts DC on that 100-watt light bulb, it's going to be just as bright and dissipate the same amount of power as you put 120 volts RMS, which is what you got out of your wall socket. The voltage you're going to see out of that wall socket, if you actually measure it, is going to have peaks of like plus or minus, I forgot the exact number, 180 volts. Over 300 volts peak to peak. But the area under the curve, which is what root mean square gives us, would be the equivalent of that same DC voltage. So the key is that an RMS voltage will produce the same amount of heating as DC. Here's a more complicated pie chart that includes not only Ohm's law, but power. This one would be hard for you to kind of reconstruct on the back of your answer sheet, but it's a good reference with all the formulas there. So what did we learn? That power is the rate of doing work. We measure it in watts. The joule is 1 watt second. In other words, is power for a period of time. And the power equations are power equals voltage times the current, or the current squared times the resistance, or the voltage squared divided by the resistance. And those you kind of need to know. Any questions on those?
No, very clear.
Nope, I'm good.